different prices over time. Okay, so you might think about a firm starting at a high price and then dropping prices over time, or starting at a low price and raising prices, or triangulating between high and low prices, and then what we've learned so far and so on. Okay. Now, if you really wanted to get after this question, a pretty standard economic theory approach to it would be to consider a firm that's long-lived and sets prices and maximizes an expected sum of discounted flow profits. And the solution we get to that problem, we might then posit as our prediction for how firms set prices in practice. Here, I'm going to do something that's just slightly different. I'm going to think about a firm that's maximizing its guaranteed sum of discounted flow profits. Okay, and that's the whole paper. So that's the problem that I'm going to consider. I'll characterize the solution. There are, a couple of motivations you can keep in mind for considering this problem. One, you might think it's an attractive policy for a new firm, like a startup that knows very little about its demand curve, to have a policy that's robust in the sense that it gives a high payoff guarantee. Alternatively, you can think of this as just an as-if description of an ambiguity-averse firm that's setting prices every period. And I'll talk about more interpretations as I show you the results. Okay. So that's the paper. I want to, before I go to the model, just say a little bit more about what else has been said in the theory of rational price experimentation, and what's been said about the standard approach and how the approach that I'm considering today is different. So the problem of price experimentation is a multi-arm bandit with correlated arms. What do I mean by that? Each price here is an arm, and the reward for setting that price is the profit that the firm makes that period. Okay. And by correlated arms, what I mean is that when you set a price, that teaches you about demand not only at that price, but it also gives you a sense of what demand might be at other prices. So if I set a price of $8 for something, I kind of have a sense for how much I'm going to make in sales if I set a price of $7.50 or if I set a price of $8.50. Okay. And the problem is that typically bandits with correlated arms are very intractable. So outside of special cases, we really don't know how to solve them. And that creates sort of two hurdles for the literature on rational price experimentation. One of these hurdles is that we don't have a lot of papers that characterize the path of optimal experimentation for a firm that has a long horizon. So here's a quote by Merriman, Samuelson, and Urbano. They say that essentially two approaches have been taken in face of a firm that's dealing with a random demand curve. One approach formulates an infinite horizon model, and then the attention turns to the limiting expectation. A second approach is to restrict attention to two-period models. Okay. In the first class of papers, the question that is typically asked is, if the firm is following an optimal price experimentation strategy, does it eventually converge to choosing a price that an informed monopolist would set? Okay. Now, in the events where the answer is no, so some conditions on priors and the supports of those beliefs under which the answer is that you don't converge, we might be interested in knowing what's the extent of mispricing and in which directions do firm misprice. So that's a second hurdle, which is that we don't really have a model, models that can speak to that. So Aghion, Bolton, Harris, and Julian, which is another classic reference in this literature, say that when you don't have adequate learning, it's hard to understand the long-run outcome independently of the adjustment process by which it was reached. Okay, you need a new analysis for these cases. So to determine the nature of long-run behavior, you'd need to characterize the optimal learning strategy, which, as I said, is hard to do in most instances of this problem. Okay, and today I'm going to show you a problem which has enough structure and is tractable enough where I can say something about the path of optimal experimentation and also the limit. So here's just another slide that shows some of the relevant literature. The first class of papers on long-run learning, as I mentioned, are interested in this question of what are conditions under which firms eventually pick the same price that an informed monopolist would, and what are conditions under which they don't. Another way people have tried to make progress on this question is by focusing on the case where the state space is binary. So they say, we're uncertain about demand, but it's got to take on one of two shapes. By contrast, here, I'm interested in sort of thinking about situations where we make credible assumptions about what the firm really knows about its demand curve. Then there are, of course, 1 and 2 period models. The results so classic references on robust pricing are Bergman and Schlag, who really started thinking about pricing when a firm is max min or minimizes worst case regret. And then there have been papers that sort of extend this to 2 period models. And here I'll be thinking about a firm with an infinite planning horizon. And then finally, there's a large literature both in computer science and economic and operations research, but also in economics, which considers various heuristic pricing strategies or considers algorithms that are in some sense simple or satisfy certain asymptotic objectives. So a recent paper I'll mention is Cho and Libgober. So they're, for example, interested in thinking about a firm that uses an algorithm that, regardless of what the true demand curve might be, eventually in the limit chooses something close to an optimal price, and they're interested in strategies that are simple in some sense. Here, my firm's objectives is only maximizing worst case discounted sum of profits, and so I'm not going to put any outright restrictions or sort of penalize complexity. So the form of the strategy will be simple, but that'll arise just endogenously. Okay, so with that, I'm going to jump into the model. So there's a multi-period monopolist, okay, and the monopolist faces a persistent demand curve D. Initially, the monopolist doesn't know this demand curve. What the monopolist knows is the state space, omega. And here I'm going to make some assumptions about that state space. So let P naught and Q naught be greater than 0, and let tau lower bar and tau upper bar be less than 0. I'm going to assume that omega, the state space of demand curves, is the set of all curves, which are mappings from prices to quantities, for which D of P naught is at least Q naught. Okay, that's condition 1. And condition 2 says the slope of any demand curve in this set is bounded between tau lower bar and tau upper bar. Okay, if you take any 2 points on that curve. And so the interpretation is that this is a firm that knows very little about its demand curve, prior to experimenting with various prices. All it knows is that at some focal price P naught, it would make at least Q naught in sales. And it knows that there's some limits to elasticity. It knows that if it were to raise prices, quantity sales are not going to drop by too much. And it knows that if it were to drop prices, that this wouldn't stimulate demand by too much either. Okay, so beyond that, it doesn't know much about the shape of its demand curve, and it entertains the possibilities that it can take on all sorts of other shapes.
So why does why does the P0 have to be known? Why can't he just try P0 and it gets the Q0 right away? Or
that's a good question. So here it's just sort of, it'll turn out that, the results are going to extend to the case that you're thinking about too, Karl. So there are a lot of so this I'm starting out here in this baseline case where a little bit about some lower bound on what you can make at some focal price. Maybe it's sort of the interpretation. It's like you kind of know the size of the market, and then some limits to elasticity. We can think about other state spaces that capture less information or just different information. And when I go to sort of talk about generalizations of this model, I'll show you that a lot of the results actually port over to all sorts of other state spaces, though with some limits.
The elasticity is really cute. I mean, that's fine. The number 2, I was just about 1. Thank you.
Yeah.
But does the demand curve is the demand curve can be discontinuous? Second, does it have to satisfy some increasing hazard rate property to ensure unique uh,
Great.
monopoly profit maximizing
Yeah.
price?
Yeah. So the answer to the second question is no. There could be multiple optimal
Local max.
prices for an informed monopolist. Um, and first, the answer to the I think your first question was about are these demand curves downward sloping? Is that right? And
Continuous.
continuous. I see. Okay. So the answer is yes, because I'm assuming there's this tau lower bar and tau upper bar, and that if you take the slope between any 2 points, it's got to be bounded between those two numbers. And these tau lower bar and tau upper bar are less than 0, so these demand curves are downward sloping. Okay. So here's actions. So time is discrete. So every period, the firm is going to set some price, and it's going to observe demand at that price. Histories in this model are just sequences of price quantity pairs that the firm has discovered so far on the true demand curve. Okay. And I'm going to use this notation omega sub h to denote the set of histories that are consistent with what the firm has observed so far. So here's, for example, a history where the firm set a price P1. It observed that quantity was Q1. So it entertains the possibility that the true demand curve looks like this dashed red line that I've drawn here. It also entertains the possibility that the true demand curve looks like this other dashed red line. What it knows for sure is that the true demand curve can't look like this because this curve doesn't pass through the point that it's already discovered. Okay. And so the way learning works in this model is that the firm keeps learning, keeps observing more points on its true demand curve, and it whittles down the state space, throwing away those curves that don't pass through the points that it has discovered so far.
Clarify for the listeners, can you comment briefly about why you assume demand is not noisy? Because Econ 101, the guys would right away say, look, there's a random people coming to my shop and this random, and so I will never have this deterministic demand. So how would you respond to those guys?
Yeah, I mean, I think that's a fair point. I think that's just an aspect of reality that I'm going to abstract away from. So I think sampling variation in demand is sometimes a bigger issue, sometimes a smaller issue. I think if you're setting a price and you're living with that price for a long time, maybe you have a good enough sense for what your demand is going to be. So maybe this variation is small. So that's the kind of world that you can keep in mind. Um, and there's some ways to extend this so that you can sort of allow for actually some variation in demand over time or some noise in the observation. So I can talk a little bit more about that. But I think the kind of results that I'm going to be driving towards are going to be qualitative in nature, trying to make predictions about how firms set prices and what the dynamics of experimentation look like. And I think for those kinds of results, even when you make those sorts of extensions, things will in some form go through. I think if you were to say, well, I want to actually take a policy like this and implement it in practice, then you have to put more bells and whistles on this. And you have to sort of say, how exactly are you going to react to the fact that you observe demand noisily?
You just say that there are many customers and do then as if large numbers kind of abstract away from that. They're many customers. Kind of.
Yeah. Yeah. Great.
So it's a follow-up to Karl's question. So by persistent demand, you mean there is a deterministic demand curve you do not know. You
That's right.
only know it's a member of omega that satisfies these two properties.
That's right. That's right. And by persistent, I mean that this curve is not changing through time. And again, the goal is there is to just sort of focus on the question of just how do we learn in sort of the simplest setting where things aren't changing around. H sub t, capital H sub t, is going to denote the set of histories where there exists some consistent demand curve. Okay. And paths, which I'll denote by bold H, are just infinite histories, sequences of price quantity pairs that you've discovered. So with that notation, I can now define a strategy. So strategy is any map that takes histories to the next price that you would set at that history. The way I've written it here, it's I'm restricting to deterministic strategies, but this restriction's without loss because as I'll show you in my results, random strategies are not going to be optimal in this model, but it'll save me on some notation. Now a history, H sub t, and a strategy, sigma, and a demand curve D together induce a path of prices and quantities. So once you're starting at some history, so some points that you've already discovered, you've got a strategy, which is a fully contingent plan that tells you what to do at every history. And if there's some true demand curve D, you can trace out, if you keep applying that strategy, what prices you're going to discover and the corresponding quantities. Okay. And H of sigma D HT is going to denote that path. If I throw away the quantities part of this and focus only on prices, that's going to be the price path, which I denote as boldface P.
Can I ask perhaps a silly question, but I'm a bit fascinated about your space of possible demand functions because, so one would maybe say my space of interest is the space of all continuous functions that map from 0, 1 to 0, 1, right? That would be, that space has nice properties, and we know how to apply compactness theorems and things like that to that space. You haven't said anything at all about this, so I'm sure there's something in the background. I was perhaps hoping I could tease some information out of you, because it seems like a very strangely, it's a difficult way to understand how that connects with those properties. I mean, you discuss continuity to some extent, but in what sense is this space well behaved, I suppose I'm asking.
Well, it's well behaved in the sense that I will be able to characterize the optimal solution, but it's I will show you. I think I can give you a more useful answer after I basically outline the baseline model. In fact, I'll kind of get at exactly your question, Francesco, by characterizing all spaces for which my results will go through. And so that might be helpful, and that's coming. Okay, so I talked about strategies. I can now talk about payoffs. So delta is the discount factor. The continuation payoff to a strategy sigma at a particular history is just the sum of discounted flow profits associated with using that strategy at this history when capital D is the true demand curve. Okay, so you're applying this strategy. That's going to involve setting a price every period. You learn the demand at that price, and so you make profit P times D at that price. I'm normalizing here marginal costs to be 0. The results will go through, in fact, for any marginal costs that are decreasing with quantity. At any history, a strategy sigma has guaranteed continuation profit given by the following expression. So let me sort of explain, in words what it means, what guaranteed continuation profit means. I have a strategy, which is a fully contingent plan, and I've observed some points on my demand curve already. So I only entertain the possibility that whatever the true demand curve is, it's got to be a curve that passes through all the points that I've seen. And I say, if I were to use this fully contingent plan, how bad could things get for me? Okay, in terms of my continuation payoff, right? What would be the shape of the true demand curve among those demand curves that are still, consistent, plausible, that would make it so that if I were to use this strategy, I'd get the lowest continuation payoff possible. That's what this sort of guaranteed continuation profit object is, right? So you're taking the minimum over all those demand curves that are consistent at this history, right, for your continuation profit. Whatever true demand curve realizes, you're going to be making at least this much. That's why we call it the guaranteed continuation. A strategy sigma star is ex ante optimal if it maximizes the guaranteed continuation profit at the empty history. So prior to setting any prices, you ask yourself, what's this, I can say for any strategy, how bad can things be? What's the associated guaranteed continuation profit? An ex-ante optimal strategy is one that delivers the highest guaranteed continuation profit, standing at the empty history. Okay.
Suraj, sorry to buffer. Could you go back one slide? I'm not sure I
Yes.
understood that equation. So, now I get it. Sorry. Perfect.
Okay. So this is my notion of ex-ante optimality, but I'm going to work with a stronger solution concept because I want to think about a firm that's not only behaving optimal standing at the empty history, but a firm that's doing the best that it can given what it's learned at every point in time. Okay. So I want to define a notion of sequential optimality. And for this, I need to define one more piece of notation. So for any strategy sigma and history H sub, I say a history H sub t is reachable if it's either the empty history or it's a history that you could get to by you applying this strategy for some realization of the demand curve. Okay. Histories that are not reachable, you would never get to anyways by using this strategy, no matter what the true demand curve is. So we can kind of ignore what the strategy does at such histories. The strategy sigma star is sequentially optimal if it maximizes the firm's guaranteed continuation profit at every reachable history. Okay, so in particular, if a strategy is sequentially optimal, it's also ex-ante optimal because it has to satisfy this definition at the empty history. Okay, it's a question, right? You might wonder, do sequentially optimal strategies exist? And I'll construct one for you, show that in fact they do. So this is a firm that is doing the best that it can at every point in time, given the information that it learns.
Here I have a question. I don't really understand. So in period 5, I'm taking the optimal one. So this was maybe optimized because of behavior in period 0. But now it turns out it pans out in period 5 that it's not so worse. I might have an incentive to change my strategy. I would have thought you had a maximum that's conditional on T, and then so what? So can you help me there?
Yeah, so it's so certainly in this model, you can learn things and you can be surprised by what you learn. And the solution concept is saying that regardless of what surprises you encounter, you should be doing the best that you can from that period onwards, and that should not be inconsistent with doing the best that you could ex ante. That's what sort of sequential optimality is imposing.
I didn't see in the definition, but that's the standard definition, right? Anything that's optimal in period T would also be optimal in period 0, but then it would require a T in this. So I would have thought you define sequential optimality for each T and then show that, and so say something sequential optimality if for any T that pans out, but maybe that's what you're writing here.
I think that might be so the way that where the T is appearing here. So it's sort of you're requiring this at every history H sub T, and you're taking and once you learn some stuff,
I see.
that's sort of captured in the set of consistent demand curves.
Right. So it's only from T on the omega HT I overlooked. Yes, that's okay. Now I see it. Good.
Okay. That's the model. Let me talk about the results now.
Just a sec. I just wanted to
Yes.
clarify this once more. So what happens over time is that you can exclude some more states, right? So then that changes what your minimum is. Is that what's happening?
That's right.
I see. Okay.
Yeah.
Thanks.
And that's showing up over because you're taking the min over only those consistent demand curves at every history. Okay. So here's a simple pricing strategy. I'll call this a linear pricing strategy. The formula is not important because I'll just show you this in pictures shortly. What the strategy is going to do is it's at every history, it's going to posit some artificial demand curve, D sub H sub T, and then it's going to set the price that maximizes monopoly profits under the assumption that that artificial demand curve is actually your true demand curve. Okay, so that's what the linear pricing strategy does. This is how it behaves. So suppose this red curve here is your true demand curve. Period 0, the linear pricing strategy pretends as if this blue curve is the true demand curve. The blue curve is a kinked demand curve that passes through points P naught and Q naught, which remember, what do you know about the set of demand curves? You know that at a price of P naught, you would sell at least Q naught units. Okay, so there's a kinked demand curve with a kink at P naught, Q naught. Above P naught, the demand curve is as flat as possible, right? So this is given by tau upper bar. And below P naught, the demand curve is as steep as possible. This is given by tau lower bar. And you pretend as if this is your true demand curve, and you set the corresponding optimal price P1. Once you set this price, you learn, of course, that your demand is not D of P1, it's Q1. Okay, so period one, what do? You draw a kink demand curve with the same slopes as before, but now with a kink at P1, Q1. You pretend as if this is your true demand curve, and you set the corresponding optimal price P2. Once you set that price, you learn that demand at that price is Q2. So next period, what do? You draw the same kinked demand curve now through P2, Q2. Note that you know for a fact at this history that the blue curve cannot be the true demand curve because it doesn't pass through P1, Q1. Okay, but that's fine. This is just an as-if strategy. You behave as if the blue demand curve is the true demand curve, and you set the corresponding optimums. This is the linear pricing strategy, and it's memoryless, meaning that it doesn't depend on prices and quantities. It only depends on the current. So now let me show you some results. Proposition 1 is that the linear pricing strategy is sequentially optimal. I want to define a notion of uniqueness. I say a strategy is essentially unique if I say the optimal strategy is essentially unique if for any two optimal strategies, sigma 1 and sigma 2, and any demand curve D, both strategies lead down the same path of prices and quantities. Okay, so they might be doing weird different things at histories that are not reachable, but on path, they will always trace out the same prices and quantities. Proposition 2 is that the sequentially optimal strategy is essentially unique. Okay. And I'll show you one more result. Say prices always rise under strategy sigma if for any demand curve D and along the path H, prices are increasing on path. So it doesn't matter what demand curve realizes, the prices that you set are always weakly increasing on path. And similarly, I'll say profits always rise if these flow profits that you're making are also increasing on path. Proposition 3 is that prices and profits always rise under the linear pricing strategy.
Could you elaborate this proposition 3? From the picture, when initial estimated kinked demand is inside of actual demand, I can see that. Suppose this initial estimated demand, this kinked demand is outside of actual demand.
Yeah.
Could you show me how this increasing property can be preserved? I thought it may decrease over time.
I don't know that the increasing property is going to be preserved in that case, because then, so I'll give you the intuition for what happens. So in my state space, you know that at a price of P naught, you'll make at least Q naught, which is why you're going to be inside.
So the proposition 3 depends upon the initial condition where it starts from.
For sure.
So it's not
in the world that you're operating in, you might get an initial decrease, and then you might have increasing prices and profits after that.
So I think that proposition 3 missed some conditions. It's not always so.
Under my state space, it's always going to be true. So again, the set of demand curves that I'm allowing in my state space are those where at a price of P naught, you regardless of what demand curve you're on, you're at least going to sell Q naught units.
Oh, so you have to start from that particular demand.
That's so you know two things about your demand curve. You know that if you set a price of P naught, you sell at least Q naught units. Maybe you sell more, right? But every demand curve satisfies that property. The second property is that there's some limits to how sensitive demand is to changes in prices. And you know what those limits are. Under every such state space, proposition 3 is held. And I'll give you the intuition for it now.
Can I get further clarification? So the initial price has to be P0, and the initial demand that you would.
Can I interrupt you there? So the initial
Yeah.
price is not P0. Yeah, the initial price is P1. P0 is just something that you know. You know
Okay, all right. Sorry,
the focal price at which you know that you'll sell at
right.
least.
It's where the kink is, because
That's right.
you are assuming basically you are assuming worst case scenario. So in a way that gives you the kinked demand curve. That's those taus give you exactly how what the slopes are on the two things.
Yeah.
So you are essentially assuming a particular case of and so if one wanted to do the Bayesian thing here, then things would be much more complicated because you don't actually have a shape to work with, which you have. Would that be a fair way to put it?
Yeah, I think so.
Okay, all right.
Great. So let me just make a few comments about interpretation, and then I'll get to just the proofs of these results, which are fairly straightforward, and that'll give you the intuition for what's sort of driving these rising prices and profits. Okay, so I started out the question of the paper being, how do firms set prices in practice? I have this model, and I want to sort of now match some of the features of the optimal strategy here to pricing practices that we observe. So one way of answering the question of how do firms set prices is to go out and just ask them. And this is what Truman Bewley does in a recent book. This is 2025, not 2005. So he interviews a bunch of firms, and in particular, he interviews a lot of firms in monopolistically competitive industries where strategic concerns are kind of more muted. And what he finds is that producers of highly differentiated products seldom reduce prices. They instead tend to sluggishly raise prices over time. And not only that, when he talks to managers at these firms, they typically say things like the following. They say that, demand is going to respond little to price reduction, but a price increase might so offend buyers as to reduce demand sharply. Okay? So they have in mind some sort of kinked demand curve. So they're worried that if they drop prices, they're not going to stimulate demand much. But if they raise prices, they worry that sales will fall by a great margin. Truman says, we would want to understand if this is really some sort of empirical regularity, that these beliefs are in some sense true and this is happening everywhere, which would be really surprising. Maybe one answer is coming through this model. It's saying, no, it doesn't have to be the case that demand curves actually look like that. It's just if a firm is maximizing this sort of robust objective, it behaves as if its demand curve were kinked, and it does that at every point in time. That turns out to, in fact, deliver the optimal forward-looking strategy for a firm that's maximizing its guaranteed profits. Okay. I'll just say one more thing, and then I just in that same vein, I want to just say that these are not just in the interviews that Truman Bewley does. These are also if you talk to management consultants, they'll say similar things. So this is just a quote from BCG. They say that many executives assert that pricing is a zero-sum game. If they raise prices, the lost volume will negate the effect on high margins. If they lower prices, the additional volume will not be enough to compensate. Okay, so this is sort of commonly observed as kind of a source of price rigidity for managers at a lot of firms. Go ahead.
Yes, no, I was wondering the importance for the rationale that your model provides of these quotes. Okay, comes from the fact that P naught Q naught is fixed arbitrarily below the demand curve at some point at the beginning of the game.
Mm-hmm. Yes,
because that seems crucial. No, I mean
that's crucial. That's going to be crucial for just the fact that prices are rising throughout and initially also after the very first step prices rise. It won't be crucial if you sort of look at just if you ignore beyond the first period, you can sort of play around with this assumption and you get that prices are going to be rising after that. And it's not going to be, the P naught Q naught is not particularly crucial to the nature of the kink demand curve either. Because that arises at all future histories as well, once after you've discovered some points on the demand curve. If you don't want to start out with the assumption of the firm knows this lower bound, you might my state space kind of captures is trying to capture a firm that has never set prices in the first place and kind of makes conjectures and says, I know if I'm selling this new protein enriched cereal. I know if I start out at a price of $8, like every other cereal manufacturer, that I'm going to make at least 10,000 units in sales. That's why I kind of got into this business. So that's sort of a conservative lower bound. Alternatively, you can also take the perspective of a firm that has set a price before, but it's never experimented beyond that. Such a firm actually now knows, P1 and Q1. It starts out at such a history, and it's trying to experiment beyond that. There too, you get these kinked demand curves. Right. And for the same reasons as in the present model.
Yeah, but I mean, in a dynamic environment, because the demand may change at some point. I mean, you can perfectly have decreasing prices, no?
Okay. In a world of demanding with time varying demand, I'm totally with you. And so in some sense, you might say, saying prices rise all the time is, maybe they rise often, but we definitely see instances where they fall. And I think the way I would capture that in this model is doing exactly what you said, which is say, look, we were started out. It might shift sort of decreasing prices as well. Okay.
So Suraj, just very quickly,
go ahead.
I'm not sure how this quote confirms or this. I mean, this seems to be a quote that says prices are in equilibrium. I don't. If I raise that, I would be making less. But how this quote, how to even interpret this quote as something support. I mean, the previous one, yes, but not this one. I don't. Anyway, maybe we'll discuss that at the end of a talk. But
my interpretation of this quote, just very quickly, is just that these price setters are acting as if their demand curve is kinked. Now, they might say that even if it is kinked this way, maybe, like I still know that enough to say I can make more by raising prices, which is what's happening in my model. But this is just to say that it's not uncommon for managers to act as if their demand curve is kinked, and that's the aspect that I'm trying to get. And in response to this, consultants and VCs often suggest heuristics that kind of rhyme with the strategy that I'm suggesting. And what they will typically say is that you should raise prices over time. So if you go to, so Y Combinator is one VC. If you go to their website, they say there's a lot of uncertainty about demand when you're a startup. The best way to learn about what your demand curve looks like and find the price that you should be setting is to apply the following heuristic. You keep raising prices by 5% and keep doing that until at some point, a 5% increment in price is going to lead to a 20% reduction in sales. Once you've reached such a point, stop raising prices. You found your optimal price. Okay, so that's a heuristic that they're suggesting. If you speak to management consultants, they will also say typically you should raise prices, and we find that when firms do raise prices incrementally over time, they make more profits every step of the way. My strategy seems to kind of look like this, but it has an economic justification in the sense that it's the unique strategy that maximizes payoff guarantees. Okay. Last slide of interpretation. I think the model gives a very simple mechanism for rising prices. A common opinion, if you go out and survey people and ask why are prices of various things going up, something that they like to say is that greedy firms raise prices to increase profits. And this is a kind of difficult story to rationalize because you would say, well, if the greedy firm knew its demand curve at the start, then it would choose its monopoly price and it would stick to the monopoly price. And on the other hand, if the greedy firm didn't know its demand curve, then it should experiment conceivably with price hikes and price drops. And sometimes it's going to, as it learns about its demand, make more in profits, and sometimes it makes less. By contrast, Proposition 3 sharply rationalizes this naive intuition because it says if what the firm is after is maximizing guaranteed profits, then it's going to observe rising prices and profits every step of the way. And that turns out this happens despite static costs and demand, and because that's the unique way of maximizing your profit guarantee. Okay, so now let me show you the proofs of these results. And the idea is going to follow from the fact that this linear pricing strategy that I've shown you coincides with the myopic strategy on path, and then the myopic strategy is going to turn out to also be the forward-looking strategy in this model. Okay, so that's what I'm going to show you. So at any history, denote the lower envelope of all the consistent demand curves at that history by D lower bar. Okay, so this is, you say, how bad can demand be at any price? The answer is given by D lower bar, right? The myopic strategy pretends as if this lower envelope of all consistent demand curves is the true demand curve, and it sets the corresponding optimal price. And so at the empty history, D lower bar is exactly what I've shown you in the linear, the artificial demand curve that's used in the linear pricing strategy. Okay, but at other histories, it's going to be a more complex piecewise linear function. Okay, now it's easy to see that under D lower bar, prices always rise. And why do they always rise? At every point in time, you're making the most conservative estimate possible of what your demand can be. And so if you're ever surprised by how much you make in sales, you're only surprised to the upside. You sell more stuff than you thought you would. If you sell more stuff that you thought you would, this windfall of inframarginal consumers makes it attractive to then raise prices by $1 because now you can collect that dollar on more people. So you're considering only raising prices, never dropping them. But when you raise prices, you do so conservatively. Why? Because you're worried that demand is very elastic when you raise prices. Okay? But then when you conservatively raise prices, again, you're surprised to the upside by how much you make in sales. You raise prices again, and so on. Why do profits also increase at every point in time? Because this is the myopic strategy. The myopic strategy, you have the option of sticking to the same price as you set last period. The only reason you would change the price is if you could make more money that very period. And so that's going to deliver the fact that flow profits have to be increasing through time as well. You only change price if you're guaranteed to make more that very period.
So
Okay?
Can it be stuck at the local maximum?
Yes. And I'll tell you I'll tell you where this strategy converges and where that point will be relative to the price that an informed monopolist sets. So far, I've given you results of path of experimentation.
So
go ahead.
This procedure can give you long-run average profit significantly away from true maximum profit.
Certainly. Yes.
Especially when there is a local maximum, which is not global maximum.
Certainly. And in fact, this is kind of, this is the one point of departure, for example, from your work, where the solution concept is to, regardless of the demand curve, eventually be best responding. Here, I'm thinking about a firm that's kind of trading up. It says, my goal isn't to just kind of eventually find an optimal demand curve. I have to survive this first year. And I have to survive the year after that. And so I want to do something that's kind of, it's not just about the limit, but I want to be making good profits along the way as well. And that's going to lead to this trade-off.
I think you should give us some rationale that why the profit maximizing firm want to use your algorithm over algorithm by Karl and Roughgarden and those guys, for example, which is also known to find the true maximum in the long run.
Yeah, I think it's just I think they're just different worlds that we're operating in. And so how I think about it is, if I'm selling diapers on Amazon, then maybe I can change the price 1 trillion times over the course of 2 days. And so the goal there is to just really search very extensively and eventually get to an optimal price and set that price for a long time. On the other hand, I think there are a lot of businesses where prices tend to be sticky and the opportunity to change prices come more infrequently. So I'm selling some beverage through some retailer. Might be that, I negotiate some price and say that's the, I have this new beverage. That's the price that I'm going to set. And I have to live with that price for the next year before we get to sort of go back to the retailer and say, now I want to change the prices again. In the world where you're changing prices slowly, I think you're concerned with the path of experimentation and not just the limit of it. And that's the kind of world that I'm thinking about. Okay. So this is this is saying that under the myopic strategy, prices and profits always rise. Lemma 2 says that the myopic strategy actually coincides with the linear pricing strategy that I showed you on path. Okay? Why is that? Well, I already argued under the myopic strategy that I would raise prices at this history, right? I would only consider setting a price higher than P2 and never lower. Now, if I took this blue demand curve and I lopped off some of the demand in the bottom part of that curve, that's a force that's going to make me that's going to push me even further to setting higher prices, right? So if it wasn't attractive to set low prices when the demand curve looks like this, certainly it's not attractive to set low prices when the demand curve looks like this. Okay, that's case one. Case two, so I found myself at a history here where at the empty history, I wanted to set a price of P1. If at the empty history I wanted to set a price of P1, that means setting a price that would have put me on this yellow highlighted region was dominated at the empty history, right? Now I got a windfall of sales and I realized that at P1 I sell Q1, so I'm making even more than I thought before. I certainly would not want to now go back and set a price that puts me in that highlighted region, right? And so if I never want to set a price that puts me in that region, if I ironed out the demand curve to look like this, a fortiori, I don't want to set a price that puts me in that region. And so these are basically the arguments that allow me to kind of iron out these multiple kinks and show that, in fact, the memoryless strategy that I showed you, this linear pricing strategy, is the optimal one. You only ever need to keep track of the latest price and quantity. You can drop all the previous prices and quantities because they're not going to be relevant for setting the next price. Okay. So what did I argue? Under the myopic strategy, prices and profits always rise, and the linear pricing strategy coincides with the myopic strategy on path at reachable histories. Okay. Finally, I want to argue now that the myopic strategy is sequentially optimal. Okay. And so there's two steps for this. Step number one, at any history, the payoff, the payoff that you would get if you used any other strategy and you were in fact facing the lower envelope of demand curves, if that were the true demand curve, would be weakly lower than if you were using the myopic strategy and facing the lower envelope of consistent demand curves. Because the myopic strategy best responds to facing the lower envelope of consistent demand curves. Okay, so all this is saying is if you're being pessimistic about what demand might be, if that in fact if that corresponds with reality, if the true demand curve is that lower envelope, then the best you can be doing is use the myopic strategy. Any other strategy would sort of set potentially a price somewhere else, get lower profits, and that's going to be worse. Conversely, if you're using the myopic strategy, then the worst thing that could happen to you is that the lower envelope of all consistent demand curves is the true demand curve. Why? Because if you faced any other demand curve, remember, the only thing that could happen is you're potentially surprised to the upside by sales, so you make more profit that period. But lemma 1 says that the myopic strategy, in fact, will also make more profits in every future period, right? And so any demand curve that you face that's not the lower envelope of consistent demand curves, you're going to be making weekly more. Okay, so both of these things together deliver that the myopic strategy is actually the guarantee maximizing strategy at every history. Okay, and then the propositions just follow from combining these various limits. Everything I showed you so far is about the path of experimentation. So it's sort of talking about what are the path of prices and profits. I will now want to tell you kind of where this strategy is going to converge. Okay, so for any demand curve D and an
Could you
optimal
clarify
strategy.
your sense of the experimentation? Because I feel a little bit uncomfortable about what you said, because world is basically deterministic, and there is
Yes.
no intentional active experimentation a la
Yes.
this Four Guys paper. So what do you mean by experimentation? In each
Good.
period, you make like a intentional optimizing solution given your belief.
Yes.
But where is the room for experimentation in your framework?
It's in fact it's what's happening here is you're totally right. Any learning that happens here is totally incidental. So we, typically for when we're maximizing, when we're dealing with some sort of, bandit with correlated arms and we're maximizing expected payoffs, there's this, exploration exploitation trade-off. And sometimes you sort of give up profits this period to learn more about your demand curve, which will help you in future periods. And the nature of the result here is that if what you're going after is profit guarantee maximization, that it's actually exploit is going to, which is the myopic strategy, is also going to coincide with the forward-looking strategy. And so I think an observation of this paper is that being worried about profit guarantees shuts down worrying about the future. That intuition isn't complete, because it turns out that it's not just being profit guarantee maximizing. It's going to be a combination of profit guarantee maximization and the geometry of the state space. And what I'll show you in the general result, the general case is a result that will say something about what the condition on the state space is for the myopic strategy to also coincide with the forward-looking strategy.
Suppose we restrict further this omega.
Yeah.
Just include demand curve that satisfy the increasing hazard rate property so that it has a unique global maximum. I think your procedure will find global maximum eventually. Am I right?
I don't think so. So I'll give you the logic of the next result, and I'll tell you why you might stop short.
Oh, that is surprising result then.
So and then, by the way, the fact that you don't necessarily find a global maximum is not sort of unique to guarantee maximization. So there are conditions, even if you're an expected payoff maximizer, there are conditions under which you do get stuck at local maxima. And so some of the papers that I've cited in literature find instances where you do get stuck at local maxima.
Oh, no, look, if the demand curve satisfies this regularity condition of Meyerson, then we know it has a unique maximum.
Yep.
So,
well, so one such paper, for example, is the McClellan paper that I cited, where you say I face one of two demand curves, right? Two linear demand curves, and I still get stuck. There's some priors under which I kind of stay at this sort of intersection of those two curves, and I never fully learn. So there could be confounded learning. Let me tell you about this long run result. So for any demand curve and for any optimal strategy sigma, I'm going to say that prices on path converge to a long run price P infinity D. Okay, so that's going to be that's the limit of experimentation when you are applying this an optimal strategy and the demand curve is D. And there can be multiple, of course, optimal prices for an informed monopolist. I'm going to denote the smallest of these by P star D. That's if I know my demand curve, what's the price that I would set? And that the answer to that is P star D. I'm going to say that there's underpricing if P infinity D is less than or equal to P star D. And I'm going to say that there's price rigidity if I always set the same price, if I never change the price. Okay. Proposition 4 says there's either generically, there's either going to be price rigidity or underpricing, okay, for any parameters of the model. And so, the, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31 32 33 34 35 36 37 38 39 40 41 42 43 44 45 46 47 48 49 50 51 52 53 54 55 56 57 58 59 60 61 62 63 64 65 66 67 68 69 70 71 72 73 74 75 76 77 78 79 80 81 82 83 84 85 86 87 88 89 90 91 92 93 94 95 96 97 98 99 100 101 102 103 104 105 106 107 108 109 110 111 112 113 114 115 116 117 118 119 120 121 122 123 124 125 126 127 128 129 130 131 132 133 134 135 136 137 138 139 140 141 142 143 144 145 146 147 148 149 150 151 152 153 154 155 156 157 158 159 160 there's a question of kind of normatively, would you prescribe this strategy to a firm? And I think that the answer is it depends on what the firm's preferences are and if they're truly that risk averse. And then there's also the positive question of, do firms typically underprice? All of the sort of when I was referencing kind of these interviews that Bewley did and things that these VCs and management consultants say, what they find is that typically firms tend to underprice, and so that's kind of one way of understanding this result. And the proof of this proposition is as follows. So suppose you find yourself at this history and you're considering raising prices to P2, because P2 is the optimal price when you face this blue demand curve. Then P2 is going to continue to be the optimal price when you remove this kink and just consider this linear demand curve as well, right? Because linear demand curves have a unique optimal price. What that tells you is that because P2 is the optimal price, and if the blue demand curve were the true curve, you would never set a price below P2. That means also setting a price of P2 would dominate the revenue that you would get if you set a price of P1 or lower under the true demand curve. Because this blue curve here dominates this red curve. And iterating this argument is going to tell you that whatever is the lowest monopoly price, it's always got to be higher than whatever this strategy converges to on path. Okay, so if prices ever strictly rise, they're always going to be below, weakly below the price that an informed monopolist would set. Okay, and essentially you're being pessimistic about what elasticity could be. You're worried that you raise prices that you're going to lose a lot in sales. The true demand curve might not face that property, and that's why because price is always rising, you stop too soon. Okay. The last proposition that I want to show you in this baseline model is the following. We can ask ourselves, if we were to use this policy, so how far away would be the revenues that we eventually achieve from those that would be achieved by an informed monopolist? And Proposition 5 gives an answer to this. So it's taking the ratio of the flow profits that you would eventually be making by using this guarantee maximizing strategy to the flow profits you would be making if you actually knew what the demand curve was. And Proposition 5 says this ratio is always greater than or equal to 4 tau lower bar times tau upper bar divided by tau lower bar plus tau upper bar squared. If tau lower bar equals tau upper bar, then we know exactly what the demand curve is. This ratio is 1. We would be making the optimal price. But in general, when there's a gap in between tau lower bar and tau upper bar, the amount of profits that we can guarantee relative to what you would be making as an informed monopolist is going to be a ratio smaller than that. Let me just give a sort of a word of interpretation. So one way, I talked about this policy.
Sorry, Suraj, just to clarify, I was going to ask you, I would have been interested in knowing when P d infinity was strictly lower than P star d, right? Because that would be, and I guess you're not showing that to us because you don't know, but this thing seems to be a way of kind of what you really care about is revenue ultimately, which is what you have, or profits. So actually, in a way, this is saying, in general, that thing, if we're looking at it from a revenue and not a price perspective, it is less than 1. So you're not really converging in that. Is that how to think about this?
Yeah, that's a way of interpreting this. Exactly. Yeah. And I think if you think about I'm thinking about a firm here that is sort of literally maximizing its guaranteed profits, but I want to give a broader interpretation. I think even a firm that has totally different objectives than profit guarantee maximization might be interested in Proposition 5 for the following reason. I think it might be useful for a firm to understand how much it can guarantee itself in profits. And Proposition 5 gives an answer to this, right? If your objective was something totally different, but I came to you and I said, you tell me what you know about elasticities, and then based off of what you told me, I can tell you that you would actually get 90% of what you would get had you known your demand curve if you follow the guarantee maximizing strategy You might say, well, even though I wasn't, I'm not strictly speaking a profit guarantee maximizer, 90% is really good. And so that sounds like an attractive policy to me. Alternatively, if you tell me what you know about elasticities and I tell you you can only guarantee yourself 30% of what you would be making if you knew your demand curve, you might say 30% is not a good enough guarantee. And what this answer tells me is that I should go back and I should do costly consumer surveys and market research to sharpen my understanding of what elasticities are in this industry. And so Proposition 5 might be useful for basically this meta decision problem of should I, do I find the profit guarantee maximizing strategy attractive, or do I want to go back to the drawing board and learn more about my demand curve in other ways?
Raj, your answer there was actually kind of like the competitive ratio. So if I really bought that, I would change my objective and not look at the guarantee, but look at the competitive ratio.
Yes.
So what you're saying is that and you could think about regret too. You could just say that I'm not interested in the lowest regret, but a regret below something. I'm interested in competitive ratio that is above something. Then actually you have a simple strategy that works irrespective of the delta, and that's how you would be selling it.
Yeah, that's right, Karl. And I think in fact it would be very interesting to characterize kind of in this kind of environment what a firm would do if it was after maximizing minimizing worst case regret or maximizing its competitive ratio. The approach that I took here is to sort of consider a firm that sort of, seems to be sort of really risk averse and kind of make a more positive prediction, but then come back and say, well, what does this sort of competitive ratio look like in this world? I think it's very reasonable to think about a model where you say, well, if that's what we're after, let's directly maximize that and see what those strategies look like. So I think I'm out of time. So I'll should maybe open it up for discussion here. I want to just sort of, highlight kind of where else the paper goes. I was responding to In-Koo saying that in general, it's not going to be the case for other state spaces that the optimal strategy coincides with the myopic strategy. That happens in the baseline case, but there's worlds in which this is not true. And this happens precisely because, if you consider a world where you know that the demand curve is one of two different curves, then experimenting a little teaches you a lot. And so learning is going to be more valuable in that kind of, for that kind of state space. Learning is less valuable for my state space because you entertain such a rich set of possibilities for what demand looks like. And when you have a lot of uncertainty and learning has less value, that pushes you in the direction of just making more profits today. And if anything that I learn is incidental. And so where the paper goes, it gives a necessary and sufficient condition on state spaces for the myopic strategy to be to coincide with the forward-looking strategy. And when that condition isn't satisfied, experimentation will have value. The use of that theorem is that we can now go to other state spaces. We can think about, the space of concave demand curves or convex demand curves, and also characterize optimal strategies in that world. So with that, let me just summarize. What I try to do here is start with credible assumptions about what the monopolist knows, and then derive policies that maximize profit guarantees. I showed that at least in the baseline case, the strategy is myopic, so it ignores the future, and memoryless, so it ignores the past. And I showed you a result that can quantify when these guarantees are good enough, and if they're not, maybe give you an indication that you should go back and learn more about the demand curve through other means beyond price experimentation. Okay, so I'll end that here, and then we can have a discussion.
Great. Thanks a lot, Rats, for the presentation. So I will open the floor now for some comments, first by the panelists. So In-Koo, do you have any comment or question?
Yes. Could you summarize your research objective of this exercise? Because right now there are many alternative algorithms they can perform better in a certain sense.
Sure.
So kind of like Rough Gardens papers are kind of benchmark.
Mm-hmm.
And the Bevis and ZV has another algorithm that can converge to true optimum.
Mm-hmm.
I think you should be very clear about what is the advantage or what is the edge this particular algorithm has over existing one, despite the fact that it may not achieve true optimum under very idealized conditions.
Yes.
I think that's something you should clarify in the introduction.
Mhm.
Also, it sounds like your exercise is not the exercise for when delta, the discount factor is close to 1, but it's more like a given delta, how it works. Am I right?
Mhm. Yes.
So
So, yep.
in such a case, the conversion speed is a very important considerations because experimentation can be very costly. So in such a case, I might want to see some result on the data complexities, or how many
Yeah.
observations do you need in order to achieve uh, uh, optimum in a well-defined sense. Other than that, uh, I think you answered all my questions.
Thanks for those comments, In-Koo. So on the second point, I don't have anything to say other than I agree with you. I think it's a very natural question to ask about convergence speed, and so I'm interested in deriving results that look like that. On your first point, yeah, what is the research objective? I think that's a very good question. And I think certainly the goal is not to horse race my algorithm against so many other algorithms that have been derived in computer science and operations and other fields, and say that, you know, this is better or worse in any way, or yeah, right. So and in fact, I don't even know how to make those comparisons without actually talking about what the objectives are.
Yeah.
The goal here is really to make predictions about firm behavior. I think that um, kind of if you the results that existing results that we have on rational price experimentation are limited in the sense that you can't characterize the path of experimentation for a long-lived firm. I was interested in making a model that I could call in some sense rational to make predictions. I'm rational in the sense that my firm has an objective. It forms a fully contingent plan, and at every point in time, it wants to stick with that plan. So the goal was that. And I think you can't achieve that goal if you have as your objective something like convergence or low asymptotic regret. And I think the reason is quite simple. I think if those are your objectives, that's a very reasonable thing to consider for a lot of situations. Normatively, if you say, how should we set prices? I'd probably say some algorithm like that might be useful. But on the other hand, they make no predictions about behavior. And the reason is because you can take any one of those algorithms, do something totally crazy for the first trillion periods, and then apply that algorithm, and it's going to have the same asymptotic guarantees. On the other hand, I wanted a model that's going to give me a sharp prediction about behavior on path. And so I think this was my attempt to do such a thing. While sort of
I think to do so, you definitely need a result on the convergence speed.
Mhm.
Actually, if you run some numerical simulation of rough garden, you don't need trillions. It's just it works quite well.
No. Working well is but again, working well is a totally different. I'm sure it works well, and I'm sure it works well quickly. All I mean to say is that the way we typically sort of make predictions about behaviors of economic agents is we say they're maximizing some objective, and then we characterize what that strategy is. I'm saying that I could insert in their algorithm just this noise where I do something crazy for a trillion periods, and it's going to give me the same guarantees. That's just to say that my model, I think that algorithm might be very suitable in practice. But I think on the other hand, the algorithm itself doesn't make, in the sense that I would like, predictions about behavior as the way economists typically try to make
Fair
predictions.
enough.
I would like to disagree. So I think what you're doing is you're taking an objective, a clear objective, the delta. And if In-Koo claims that with very few observations, you get close to the maximum, all he's saying is it seems like with a lower delta from 1, these algorithms that are discovered, minimize maximum regret or keep the regret lower. So we can actually talk about what In-Koo says in mathematics. The only thing is we don't have a result on this. So we cannot use simulation for that. We need a result. So I don't know of a result for any given delta on whether that happens. So there's an literature out there, of course, to understand what happens if delta goes to 1. That's exactly these algorithms, right? And that's good if you have a lot of data. But conversion speed, I'm not really so happy with it in general because you just show it's optimal. It's not about conversion. They're not interested in the long run. Now, if you want to, or medium run, if you would think about conversion, maybe you would say the first 5 periods are for free, and then you can do something. And that would be really experimentation. But that's not what you have here. So I really would disagree. I think this is a very clear objective about ambiguity, not about risk. About ambiguity, there are 3 ways of thinking about these days. I think about max min, min max regret, and competitive ratio. And you have one of these 3, and one of these 3, this is the unique behavior, essentially. So there's no way around it. Again, what In-Koo is talking a little about is he loves this other one a lot, which is a good idea. That means it seems to be room for research on regret. But it's not that it would not be descriptive. It would be very descriptive. Have delta as a half, and then you can basically find the optimal thing and have a descriptive and know the optimal solution and be very descriptive. So that paper would be as descriptive as yours. I think there's no difference. It's just as a different way of thinking about the problem.
By the way,
more common. The other one I want to say here is about the title. So again, cool paper. Really cool paper. And I just think the title misses the point because it's not about experimentation. It's a little also what In-Koo Cho maybe was caught into. I don't know. It's like, it's not about experimentation. It's maybe you would have as a main insight, should we experiment or not? You say, no, we should not. But you didn't ever talk about that. So the title is away from what you're doing. This is just about, under ambiguity, how to price under ambiguity. And that's what the answer of the paper is. Now, the consequence is you don't need to think about experimentation, yes, but in your whole way that you present, you never emphasize that. So I don't know why you put this. So you seem like you're long run with experimentation, but it's not about long run. So that was 2 comments because I had many questions. Thanks a lot.
Great. I agree with your second comment. I also I agree with both comments. I think by the way, to the first comment, I think maybe there's some ambiguity about the definition of regret. So I know they're used in sort of different ways. What I was talking about is algorithms that sort of are focused with some asymptotic notion of it. I think it certainly would make a lot of sense and would give exactly as sharp a prediction to think about a firm that's literally just it has some delta and is trying to minimize its worst case regret, and I think that problem is a very reasonable one to study. And I'm just trying to separate that from the way the term regret is used in the computer science literature. But yeah, no, point taken.
Okay, great. Thank you. So, do you have any questions from other members of the audience?
I have a question, but we can stop the recording perhaps because it's time.
I was going to say I had a question too, but I didn't want it recorded anyway. So.
Okay, so let's stop the recording now, and thanks everyone for coming, and
Thank you.
see you next week.